So hello everyone, I'm Norman Wildberger. We're here at the University of New South Wales, and this is a course in differential geometry, and in our last lecture we introduced or reintroduced an old method of Lagrange and Euler to basically initiate the differential calculus. And it's going to be a point of view that's useful for us in our study of curves and surfaces. So let me illustrate what was going on there with the example of a cubic polynomial. So we'll look at a general cubic polynomial. Say P equals A plus BX plus CX squared plus DX cubed. So that's a general one. And let's take a point at the point R on the line. And for us, R is usually a rational number, but if you like, you can think of it as a real number too. All right, so we're going to expand P around R, and the way we do that is we just evaluate P of X plus R. So that's A plus B, X plus R plus C, X plus R squared plus D, X plus R cubed. And then we write that out in terms of the various powers of X. So there's the constant term, and then the stuff involving X will be B plus 2CR plus 3DR squared times X. And the stuff involving X squared, there will be a C plus 3D times R, X squared, and the X cubed term just DX cubed. Okay, so then we rewrite this just by replacing X with X minus R. So we get what we might call the Taylor polynomial. The Taylor polynomial of P at R, which is just P of X equals A plus BR plus CR squared plus DR cubed plus B plus 2CR plus 3DR squared times X minus R plus C plus 3DR times X minus R squared plus D X minus R cubed. So that's just actually a rewriting of the original polynomial. It's the same as the original polynomial, except now that it's sort of expressed in powers of X minus R, and we've only used very elementary high school algebra. Basically, we've just translated the polynomial, that's all. Okay, so these various functions or polynomials that appear here as the coefficients, we can give them some names. So this, well, let me just I'll write this. So this thing here is D0 of P at evaluated at R. This one here is D1 of P at R, which is just the same as the ordinary derivative of P at R. This one here is what we're going to call D2 of P of R. And this one is D3 P of R. All right, so these polynomials, the coefficients, are polynomials in R that are derived from P by essentially differentiation, but they're not exactly the usual derivatives. So where, say, D sub K of P is the same as the kth derivative over K factorial. So if we wanted to connect it with the usual derivatives, we're almost getting the derivatives, except that there's a k factorial. So here there'd be a 2 factorial and a 3 factorial separating what's happening here with the real second derivative. So we call these things subderivatives. They're almost like derivatives, but they're a little bit different. They're a little bit more convenient to work with in some sense because the numbers involved, the coefficients involved are not quite as big. If you take the 5th derivative of a polynomial, there will be a lot of 120s in all the coefficients because of the 5 factorial that will appear. We're basically just extracting that 5 factorial out and dispensing with it. Okay, so we have the various subderivatives, and then what we're particularly interested in is truncating this expression to various degrees. When we do that, we get various approximations to the polynomial that are valid near the point R and have geometrical significance for us. So by truncating this expression, let's call it star, this expression star. By truncating star, we obtain the Taylor polynomials. The Taylor polynomials of P at R. And let's write down what they are. So we'll use T for Taylor. So at R, the 0th one, in this case is just A plus BR plus CR squared plus DR cubed. You might think of this now as actually a function, as a polynomial in X. It's actually a polynomial in X. This one just happens to be a constant polynomial. And then the next one, TR of 1, is what you get when you take the first 2 terms. Okay, A plus BR plus CR squared plus DR cubed plus B plus 2CR plus 3DR squared times X minus R. And the second one is, well, all the first 3 terms. So I'll just write this and then the same thing here. And then finally, C plus 3DR times X minus R squared. And the last one, TR3 of P of X, well, that's going to be just the whole expression, so that'll just be, in this case, P of X, because we're dealing with a degree 3 polynomial. So these Taylor polynomials are going to be, for us, geometrical, simpler versions of the original polynomial, especially valid near the point R. So, for example, here is a polynomial something like that. That happens to be the polynomial P of X equals 5 minus 3x minus 4 x squared plus x cubed. Okay, so suppose we choose some point. Let's say r equals 2. Then the value here, this will be the value t sub r of 0 of p. That's just that particular value there. So the first Taylor polynomial will be the tangent line. So that'll be t of, well, at 2, let's say, so I'll write 2. t2 of 1 of p. And then also there will be a tangent conic parabola, or maybe something like this. These are all polynomials of x. Okay, so let's have a look at, first of all, the geometrical significance of these things. So we should think about this formula as being valid. Star is useful when x minus r is very small. Okay, it's very, very small. So if x minus r is very, very small, so small that you cannot see it, then the only thing that you can see here is this constant function here, and that's the situation where we basically have our view very, very close, so close to the function that we can only see that point in question. Our face is almost right at the board. So in other words, we scale things up so that we're looking at a very, very, very small little neighborhood of r. So x would be very, very close. In that case, we only see that point. If we go a little bit further away, move a little bit further away, maybe so that we're out, out this far, there's a little bit of room, then we see a little bit more of the curve. In that case, the x minus r will be small but visible. If x minus r is small but visible, but still so small that x minus r squared is negligible, like if this is 1/millionth, maybe you can see 1/millionth, but you can't see 1/millionth squared. And you're certainly not going to be able to see 1/millionth cubed. So that means these two terms would be invisible to you, and you would only see the linear part of the function. In other words, the function would actually look to you like a line. It would look exactly like this tangent line. It would be indistinguishable from the tangent line if you had magnified it that close. On the other hand, if you zoomed a little bit further away, so you go back a little bit further, so that now not only is x minus r visible, but x minus r squared is also visible. Maybe x minus r is now a thousandth, and 1,000 squared is a millionth. Maybe you can see that. But a billionth you still can't see. So if you've gone further away, then this term here will be invisible, and you will see the function as being the parabola. It will be indistinguishable from the parabola. So it's really a question of scale, of how much you're zooming in or out near this point at r equals 2. Okay, so this thing here, of course, this is just the function evaluated at r. And if we have a look at this expression, and if we look at p of x minus p of r, in other words, we take this thing to the left-hand side, and then if we divide by x minus r, then what's left on the right-hand side will be this term here, so what we're calling d1p of r. And then the other terms, there'll be a d2p of r times now x minus r, and a d3p of r x minus r squared, since we've divided by x minus r. And if we look now at the limiting value of both sides when x approaches r, well, then these two terms are going to disappear. So as x approaches r, this and this go to 0. So we can say that the limit, we can see that the limit of p of x minus p of r over x minus r is just this number d1p of r. So in other words, this is the limit as x approaches r. So in other words, we're seeing that the standard definition of the derivative of the polynomial at the point R is captured by this algebraic business. It's just a question of looking what happens when you divide by x minus r and let x go to r. All right, so this really is the derivative of p at r in the standard way. So this is explains why this really is no different from the usual story. It's completely equivalent to the usual framework, but we don't have to go via this limiting procedure. Okay, something else I want to mention is the error. Okay, so when we approximate the whole polynomial by any one of these tangent polynomials, there's an error. And in fact, we know exactly what the error is in this kind of situation because it's just the terms that we're dropping off. Okay, so if we take the linear approximation, in other words, we use this, then the error is just this. If we take the quadratic approximation, meaning those first three terms, well, then the error is just this term here. Okay. So in terms of the diagram, if we're at some point, and the point doesn't have to be close to r at all. If we're at some point here, and we're interested in, say, the difference between the function's value at x, which is up here, and, say, the linear approximation of the tangent line, then it's given by the sum of the last two terms in our expression star. And if we're interested in the difference between the function's value and the quadratic approximation, that difference there, that will just be exactly the last term right here. That'll be d times x minus r cubed. So on this picture here, this is the tangent conic at r equals 2. This quantity here, which is d times x minus 2 cubed, if r equals 2, that's just the error between the curve itself and the tangent conic at the point 2. So notice that this is we have complete control over this error. Complete control over this error. We know exactly how far we have to go from the tangent conic to the curve itself. Okay, this leads us to a very remarkable, I think, and beautiful observation, which seems to have eluded researchers in calculus for quite a long time. It's only been discovered in the last 10 years or so, as far as I can see. So the theorem is that for a cubic polynomial, p of x, all the tangent conics the things that we're calling T sub R2 of P of X, all the tangent conics are distinct or are disjoint. In other words, none of them, no two of them meet each other. So that means if I went around graphing not just that tangent conic, but if I graph the tangent conic here, well, maybe it would look like this, and I graphed it here, maybe it would look like this. There's also an inflection point somewhere for this curve, right? There's an inflection point somewhere where the tangent actually meets the curve to order 2. It's actually the tangent conic reduces to a line. So that's also part of the story. So what we're saying is that all these tangent conics, not just the 3 that I've shown you, but all of them are disjoint. Okay, so this seems remarkable, but I think it was first only observed relatively recently. This is an observation that I believe is due to Etienne Guisse, a French geometer. And he actually described it in a video it's available on a video of a seminar that he gave at some conference, I believe. And it's relatively recent. So I also stumbled across this thing and I was also sort of amazed at it. It's really quite a beautiful thing. And let's see if we can see what it is. The proof is actually almost a one-line proof, really, from what we've said. Well, for example, let's consider this point here. Okay, there's a point there. Okay, that happens to be a point on this particular tangent conic. Let's ask what other tangent conics could possibly go through that point. Okay, so if there's some other tangent conic that also goes through that point, it means that the error is going to be the same. The error between that other tangent conic, which would pass through there, and the function's values is also going to be the same error as this one. All right? So if two tangent conics, say at R1 and R2, pass through the same point, then the errors are the same. Then the errors at that point are the same. And we know exactly what the error is. The error is d times x minus r cubed. So it would have to be that d times x minus r1 cubed has to be equal to d times x minus r2 cubed. But d is non-zero because this is a cubic. And so you can cancel the d's, and then you have this quantity cubed equals this quantity cubed. And so there's, if two cubes are the same, then the numbers are the same. And so therefore R1 has to equal R2. Well, if a tangent conic passes through a point, then it's the only tangent conic that passes through that point. It's not necessarily the case that every point has a tangent conic going through it. That's an interesting question. So this naturally leads to some questions. Is this generalized? And so a problem to think about. First part, generalize this to polynomials of degree 5. Well, and beyond if you want to. And part 2, what happens, or what can you say for quartic polynomials? In other words, polynomials of degree 4. Okay, so that's certainly an interesting story. I think it shows that this whole subject of tangent conics is largely unexplored. Right? If it had been explored, then this would have been obvious to people a long time ago. So it probably suggests that there's probably quite a lot of other interesting things that you could say for in exploring not just tangent conics, but also tangent cubics and higher tangents. We're going to see the importance of tangent conics in this course because differential geometry is all about quadratic approximations to curves and surfaces. Okay, so that's in some sense that's a broad framework for thinking about what differential geometry is. We're going to look at curves and surfaces, and we're going to look at them so carefully that we don't just want to have a linear approximation, we want to look at them quadratically. So we're going to be interested in asking, what does the tangent conic look like? And what do the properties of the tangent conic, or maybe some other conics, have to do with the properties of the curve or the surface more generally? So it's going to be very important for us to think in terms of not just tangent lines, but other higher degree approximations. And to really drive this home, I want to now generalize the discussion by going to basically calculus of several variables. And I want to show you how Lagrange's point of view allows us to think about functions of two variables in a very pleasant and natural way. All right, so we're going to go up one step to essentially second year calculus, if you like, and we're going to talk about functions or polynomials of two variables and calculus ideas in that context. And I'm going to do this in the context of an example, because I kind of like examples. But one could just as easily try to write down general formulas. But I'm going to have a look at a particular example. So I'm interested in this following function or polynomial of two variables. Maybe I should call it p also, because it's still a polynomial. It's going to be x cubed plus y cubed plus 3xy. Now I hope that sounds a little bit familiar. I hope you remember that if we set that equal to 0, we get the folium of Descartes. Okay, so that's what you get when you set p of xy equal to 0. So what we're doing now is we're introducing a function of two variables by setting this thing equal to z, and we're thinking of not having a two-dimensional picture, but now rather having a three-dimensional picture where we have an x and a y and a z, and that folium that we've just been talking about is a level. It's in the plane z equals 0. It's like a level curve, and this surface somehow is doing something, and we'd like to sort of understand what's it doing. What does it look like? What does this surface look like? Okay, so this is an example of a cubic surface. A cubic surface, and these were very much studied and loved by 19th century mathematicians. So it turns out that cubic surface is a very rich subject, very visually rich, and all kinds of wonderful things, surprising things can happen with cubic surfaces. It's much richer than just cubic curves in the plane. And we'll get a sense of that with this example, but this is just one of many possible cubic surfaces. All right, there are lots of other cubic surfaces that look completely different from this one. All right, so we're going to approach this exactly in the same way that Lagrange would suggest, except we're going to choose a point in the xy plane, say with coordinates r and s, not just a single point. Okay, and the idea is that we're still going to do exactly the same kind of thing, and let's see what happens if we do this. So we have to evaluate p of x plus r and y plus s. So that's going to be x plus r cubed plus y plus s cubed plus 3x plus r y plus s. Now we want to expand that in powers of x and y. All right, so we have to use the binomial theorem here. So there's an x cubed plus 3x squared r plus 3xr squared plus an r cubed for that first term. And then there'll be a y cubed plus 3y squared s plus 3ys squared plus s cubed for the second term. And then expanding the last business, we'll get, maybe down here, 3xy plus 3xs plus 3ry plus 3rs. It's an s. Okay, and what did we do in the one variable case? Well, we then just sort of group this together in terms of increasing powers of x. So we'll do the same thing here. Just write it out in terms of increasing powers of x and y. So what do we get? So the constant stuff is stuff not involving any x's or y's. So there's r cubed and s cubed and a 3rs. We'll put that in brackets so we've got rid of those three terms. And now the terms involving just x. Where is an x term? So here there's a 3r squared. An x, there's a 3s. That looks like the x terms. I better underline them so I don't count them twice. And then let's say the y terms. So there's a linear y term right here. So plus 3s squared y. And there's a 3rs there, a 3ry. And then there'll be the quadratic terms, starting, say, with x squared. So there's a 3r x squared there. And there's no other x squared. So 3r x squared and 3sy squared. Any other quadratic terms? There's 3xy, that's also quadratic. And now we only have the cubic terms left, and there's only x cubed plus y cubed. Okay, so that's good. So what was it that we did then? Well, we replaced the x with x minus r to get the original polynomial back. So we'll do the same thing here. We'll now take this expression, replace x with x minus r, and we'll replace y with y minus s to get r cubed plus s cubed plus 3 rs plus 3r squared plus 3s x minus r plus 3s squared plus 3r times y minus s plus 3r times x minus r squared plus 3s y minus r squared plus 3x minus r y minus s. Sorry, that's a y minus s. Plus the cubic terms x minus r cubed plus y minus s cubed. So we've ultimately just rewritten the polynomial now. This is now a Taylor polynomial about the point, Taylor polynomial of the polynomial p at the point rs. And the various coefficients, we can give them names. We can call them various derivatives or subderivatives. So we can define d0 of p to be the coefficient, well, that's the constant term. And then this thing here, what should we call that? Well, it's like degree 1. We've differentiated once, but we've differentiated in the x direction and not in the y. So we might put 1, 0 there. So d1, 0 of p will be 3r squared plus 3s, while d0, 1 of p is 3s squared plus 3r. So this is the polynomial p. This is what would usually be called the partial of p with respect to x, and this is the partial of p with respect to y. And well, then we can sort of keep going. Next one will be the quadratic thing. So d2, 0 of p would be 3r. d0, 2 of p would be 3s. And then this thing here would be kind of a mixed partial. That would be 3. And then the coefficients there would be 3, 0. P would be 1, I suppose, and D0, 3. P would be 1. So, these are sort of analogs of partial derivatives, but we can see that we can get them just algebraically without any notions of partial differentiation necessary. We're just doing the same kind of thing that we did in one variable. Okay, but what's really sort of geometrically interesting is not so much these partial derivatives, but rather the truncations. That's what's geometrically interesting. And the truncations are going to be the analogs of tangent line, tangent conic, and so on. So the sum, the tangent at RS of degree k is going to be the sum of all terms of the expression I just wrote down of total degree less than or equal to k in x minus r and y minus s. So for example, when k is 1, we're talking about the tangent plane. That's the name we'll give that. Tangent plane. It's the degree 1 term. So exactly the first row of that thing. So r cubed plus s cubed plus 3rs plus 3r squared plus 3s times x minus r plus 3s squared plus 3r times y minus s. So that will simplify a little bit. You can expand it out, and hopefully you will get r cubed plus s cubed minus 3rs plus 3r squared plus sx plus 3s squared plus ry. And then the degree 2 or less terms, well, that's going to be the tangent conic, or the 1 dimension up from a tangent conic, so the tangent quadratic. Well, I'm not going to write it all out. It's the sum starting with r cubed plus s cubed plus 3rs, and then you just keep adding all the terms up to well, up to here. All the way up to 3x minus r, y minus s. In this case, the error is just these two terms here. So we could also write it, if we want to be a little bit lazy, we could write it as the whole polynomial, which was x cubed plus y cubed plus 3xy, minus the last two terms, x minus r cubed minus y minus s cubed. It's actually a quadratic. Okay, so can we visualize a little bit what this surface looks like and what's going on here? So it's quite a pleasant situation. So in my next lecture, I will get GeoGebra out and we'll have a play around with some figures. It's very easy to illustrate these kinds of things by drawing level curves. So the original curve that we started with the folium there. So that's the case, that's sort of when p equals 0. If you look at p equals minus 1, you get something like this. So that's p equals minus 1. P equals minus 2, and sort of so on. Here's 1 and 1. It turns out that if you look at, I'll do it in a different color. If you look at the level curve when p equals 1, it appears to be a straight line. And then after that, you get things like that look like sort of like this. Might be p equals 2, something like this. All right, so we have this picture of the surface. If we're thinking of z coming out this way, all right, then the function is, I'll remind you, x cubed plus y cubed plus 3xy. That's our polynomial, and we're looking at level curves of it. So if we move in the positive x and y direction, well, these cubic terms will dominate, and it'll get big. So it's sort of coming out at us if the z is like this. So if we go in this direction, it goes up. On the other hand, if we go in this direction, it goes down, it goes negatively. Okay? And it just cuts the xy plane here, and it kind of goes down here. And then inside here, I didn't label. There's these other ones like say right here, there might be one that sort of looks like this. That might be p equals a half. And the p equals half also has a little thing like this. So there's a small hill. Here there's a small hill. Okay? So generally it's coming down here, and then there's a little hill, and then it goes down like this. We can see a little bit more by looking at this axis of symmetry. If the line x equals y, we restrict ourselves to that line x equals y, then we get p of xx equals 2x cubed plus 3x squared. And if you graph that in just the ordinary, if you think of that as just an ordinary function of x, it has a double 0 at 0. It gets a minus 3 halves. It has a 0. The derivative here, f prime of x is 6x squared plus 3x. So that's equal to 0. Now plus 6x. That's equal 0 implies x equals 0 or x equals a minus 1. So there's a max like this, so it looks like this. So that's the cross section of this surface above the line x equals y. What's particularly interesting, or one thing that's quite interesting, is this line, the blue one, the line x plus y equals 1. You might ask, well, is that really a level curve? Is that really a line that's lying in the cubic? So if we look at the p of xy minus 1, so that's x cubed plus y cubed plus 3xy minus 1, it's not entirely obvious, but this thing factors. It factors as x plus y minus 1 times x squared plus y squared minus xy plus x plus y plus 1. That implies that if x plus y minus 1 equals 0, then this is 0. Which means that that line really does lie on the cubic. The cubic is very curvy, but it does have this line that lies on it. In fact, there's a little bit more to this level curve, p equals 1. Can anybody tell me what I have missed from that level curve? It's not entirely obvious, but if you look at this quadratic and you say, well, when could this be 0? Well, this is a quadratic equation, so you could look at that quadratic equation, and if you looked at its discriminant, then you could convince yourself that there's exactly one more point, and that's the point that's sitting right here at the maximum. And that, in fact, we saw that right here. That's that point right there on that diagonal part of the surface. So this level curve is a cubic. This is an example of a cubic that consists of, well, a line and a point. So all the level curves are cubics, and it's a quite interesting thing. And obviously it's kind of an interesting question, well, what do various tangent planes look like? If you choose a point on here, what does the tangent plane look like? What does the tangent quadric look like? So before we are able to well understand that, we're going to have to appreciate a little bit more about what quadrics in general look like. All right, so Lagrange's point of view, it's a powerful point of view. It allows us to go to higher dimensions very pleasantly and easily, still only with high school algebra. In our next lecture, we'll have a look at some GeoGebra, playing around with this example and some others to illustrate well, how three-dimensional curves might look. So see you then.